Welcome to our next video in condensed matter theory. What I would like to discuss in this video is the complexity that we encounter in the description of condensed matter systems. We have seen that basically our materials are described by the Schrödinger equation, and for small systems, hydrogen atom, we have analytical solutions, and in all cases we have basically stable numerical solutions for small systems with one or two particles. Then the question is, what makes it now so hard to predict material properties of the world that we see around us? And for that we can have a look at the different length scales and energy scales and densities that we find in condensed matter systems. So let's start with a typical length scale. And in a normal lecture I would pause here and I would ask my audience to come up with typical length scales that we have in a solid. So the same here. What are typical length scales that we have? Although I'm not able to see your reactions, so this becomes a bit strange. Well, we can of course think about the atoms that our materials are built of, and typical length scales in atomic physics is the Bohr radius, which is about half an angstrom. So in a hydrogen atom, the electron sits roughly half an angstrom away from the nucleus. If we now pack two hydrogens next to each other, you would expect roughly an angstrom distance between them. In terms of order of magnitude, that is pretty much okay. Typical distances between atoms are about 2 angstrom. Hydrogen is a bit closer, some materials go to 2.5 angstrom, but that's roughly the distances that we talk about. Then, what are the typical energies that we have in a solid? And again, if you want to answer this, you can look at typical energy scales in an atom. And for the hydrogen atom, it costs the Rydberg to take an electron out of your atom and ionize it. Now in solids we're mostly not interested in photoemission or photoionization, but look either at transport or chemical reactions where you go from a bound state in another bound state. So we're having an upper limit of about 13.6 electron volt, and typical energy scales are in the order of an electron volt. That's also a reason why our sun and the earth is in the habitable zone. The typical energies that sunlight provides is electron volts, enough to make chemical reactions, but not so much that you start to break bonds and destroy all complex molecules. Then of course another typical energy scale is the temperature at which we work, and room temperature is about 300 Kelvin, but 100 Kelvin corresponds to about 10 millielectron volt. So we want to have a 10 millieV accuracy with typical energies of the electron volt scale in our system. Then we have to look at the typical densities. Well, if typical distances are of the order of an angstrom, then we say we have one particle per cubic angstrom, or 10 to the 24 per cubic centimeter. And of course, if the distance is 2 angstrom, we have basically 1/10 of a particle per cubic angstrom, or 10 to the 23 particles per cubic centimeter, which is roughly what you encounter in solids. Which means that we are dealing with an enormous amount of particles. We need to have an energy resolution of about 1 in 100. That's reasonable. And we have distances that are about angstroms large. Now, classically we can deal with a lot of particles. What makes this system so difficult? And the first problem that we encounter, or the first complication that we encounter, is that we have competing interactions. If you think of an hydrogen atom, then we have a binding energy of 1 Rydberg. But this energy can be divided into the potential energy, the Coulomb interaction between the nucleus and the electron, as well as the kinetic energy of our electron. If the electron would be free, a plane wave with momentum 0, then the kinetic energy would be 0. But now I want to bring it closer to my nucleus, and I can do this by making a wave packet or an orbital that is a linear combination of plane waves, and therefore you have kinetic energy to pay. And the kinetic energy increase for an electron bound in a hydrogen atom is exactly 1 Rydberg. Then we have, of course, the potential energy. The electron gets closer to the nucleus and therefore you gain potential energy, and the potential energy gain is 2 Rydbergs. So the potential energy and the kinetic energy are of the same order of magnitude. 2 Rydberg gain in potential energy, 1 Rydberg loss in kinetic energy, to have a total binding energy of 1 Rydberg. This is also true in solids. Our potential energies, the Coulomb interaction between the electrons and between the electrons and the nuclei, are similar distances in atoms, also similar magnitude, and the change in kinetic energy is of the same magnitude. So we have competing interactions. We cannot look at solutions of the kinetic energy and then say that Coulomb interaction is small, nor can we start from the Coulomb energy and say then that the kinetic energy is small. And then there is a very important difference between classical and quantum mechanical systems. And that has to do with things like entanglement or superposition of states. And the basic result is that quantum mechanics belongs to a different complexity class than problems in classical mechanics. And in order to show you what I mean with this, we can have a look at an example. And for that we can have a look at my PowerPoint presentation. So let's first have a look how the computational effort that we need to make or to represent states in a classical system and in a quantum system scale in a different fashion. So let's see how the number of variables that we need to write down or define a state varies between a classical system and a quantum system. So in a classical system I can have n particles. These n particles are sitting somewhere in space. They have a position and a velocity, or a position and a momentum. And therefore they are defined by 3 n variables for the position, the x, y, and z coordinate, and 3 n variables for the momentum, px, py, and pz. So in total I have 6 n real variables for n particles in my system that define the microstate of your system in a statistical mechanics fashion. Now let's see if we want to represent that system in quantum mechanics. And in quantum mechanics, a particle is represented by a wave function. Now a wave function gives a complex value to each point in space, so in principle that is an infinite number of variables that we have there. Well, that's of course not fair, because you don't have to have all wave functions, you don't have to have all flexibility in your wave function. And what we can do is we can write our wave function as a linear combination of basis states. And that's what we will do. And then we have the prefactors of our basis states as our variables to describe the system. So we have a wave function, and we write it as a sum over basis functions. And we can pick our basis functions, for example, as plane waves, and with a density or distance of about 2 angstrom per atom and a resolution of 10 millieV, you can calculate or estimate roughly how many plane waves you need to get this kind of accuracy. Well, the more plane waves you take, the better you can represent any state, so the better your energy resolution becomes, and the distances are given. And then we write our wave function as a sum of those basis states. If you want this kind of resolution, then 100 basis functions per cubic angstrom and 1 particle per cubic angstrom is roughly enough to describe your system. So that is not even 10 by 10 by 10 plane waves in each direction. And with that we can of course not only describe one particle but many particles. So if we have many particles, then our wave function of the many particle system is not just a product state of the wave functions of each particle. And what we have to do here is write our wave function as a product of all basis functions and then make linear superpositions of all those different products. So one particle in basis function 1 times second particle in basis function 1, or second particle in basis function 2, second particle in basis function 3, and then the first particle in basis function 2, etc, etc. And for each particle I have 100 different basis functions. This is binomial scaling. I have 100 n possible basis functions, one particle per 10 cubic angstrom or per cubic angstrom, with 100 basis functions. Combined, each particle can pick any of those basis functions, so in total I have 100 n basis functions filled with n particles. That gives me about 260 to the power n possible many particle states. This is the entanglement between different electrons that we can have, the superposition principle, but now in a many-body language and in a many-body system. That's of course a very different scaling. So classically we have a scaling of 6n, quantum mechanically we have a scaling of 260 to the power n. Let's have another look to see how quickly quantum mechanical systems scale, and for that we can have a look at a cluster of hydrogen atoms where we assume that the electrons are always in the 1s orbital of the hydrogen atom. So for a single atom, the electron can be spin up or spin down. So I have a Hilbert space of size 2. How many ways can I put one electron in 2 states? If I have 2 atoms, I can have either spin up on the different atoms, spin down on the different atoms, spin up, down, or down, up. That gives me 4 possible states, but then of course I can also have the electron sitting on one atom or sitting on the other atom, so I have 6 possible states. In how many ways can I put 2 electrons in 4 one-particle states? 4 over 2 is 6. With 4 atoms I have 70 possible microstates in my system. With 6 atoms I have 924 possible states in my Hilbert space. With 8 atoms 12,000, 10 atoms 180,000, 12,000 2 millions, 14 atoms 400 million, 16 atoms 600 million. So that's the exponential scaling we are talking about. And with 18 atoms we have 9 billion states in our Hilbert space. States are then described as a 9 billion by 9 billion vector, matrices and operators as a 9 billion by 9 billion matrix, and if we want to calculate the ground state we have to diagonalize this 9 billion by 9 billion matrix. Modern computers can do a lot. If you go on the internet and Google algorithms to diagonalize matrices, then RPEC is a package that has no problem in diagonalizing 4 billion by 4 billion matrices on modern architecture, but much bigger becomes a problem. So that stops you at 16 hydrogen atoms. That's very far from the 10 to the 24 atoms per cubic centimeter or 10 to the 23 atoms per cubic centimeter that we have in a solid. Of course, we don't have to do complete cubic centimeters to get reasonable agreement, but 1,000 by 1,000 by 1,000 atoms is a reasonable minimum to actually see a real solid. So that's still 1 billion atoms, which is a far cry from the 16 that you can do. And this is hydrogen. And we don't want to talk about just hydrogen. Most materials are built of heavier elements with more electrons per atom that take a role in the physics or the material properties. So that scaling is a real problem. Classically, we have 6n variables to define your 6n system. n square or 36 n square interactions. Quantum mechanically, we have 260 to the power n states in our Hilbert space and 260 to the power 2n interactions. And that, of course, is a huge difference. Just to appreciate how big a difference that is. Today, we can calculate in this fashion a carbon atom with good accuracy, which is then a Hilbert space of 600 over 6, something like 6 to the power 10 to the 13th. We have some symmetry, we have some hierarchy in the interactions, so that is doable. That is, you can bring that down on a 10 to the 9 by 10 to the 9 matrix in Hilbert space with several optimizations. Now, let's assume that our computation power doubles every year and a half, which is Moore's law. Then we need about 250 years to get to iron. If we take the same problem classically and say today we can solve a system with 10 to the 5 particles, then in 250 years, with this exponential growth doubling every year and a half, we can solve systems of 10 to the 50 particles. Well, that's almost the completely visible universe in terms of particles that we can understand. So quantum mechanically, scaling from a carbon atom to an iron atom is the same kind of complexity increase that you have classically scaling from 10 to the 5 particles, which is a tiny system in terms of condensed matters, materials. A single molecule, a single biomass molecule has more atoms, to basically the entire universe that you can solve. So it's easier to solve a classical universe than solving an iron atom, or 2 iron atoms. And that's the scaling and the problem that we have to overcome when we discuss solid-state physics and materials. Now, this problem was basically realized the moment quantum mechanics was introduced. Dirac already says we have these beautiful equations, but they are too complex to solve. And Dirac has been quoted to often say this in a putting down way. All that is left is just doing the numerics and improving the numerics to get a better understanding. And he has been criticized for that, very rightly. And Anderson has put that in a very nice way. Because it's not just solving the equation and defining better mathematical methods to solve that equation. One thing that happens when we go to these hugely complex systems is something that we call emergence. New phenomena build up out of these complex interactions that are highly unintuitive to understand from the very simple laws that build up your system. It's not saying that these simple laws are wrong. Sure, those are the microscopic interactions that we deal with. But understanding how a complex system behaves just based on its microscopic constituents is far from trivial and a very fundamental question. Especially when you have things like emergence, where very non-intuitive results can happen. And that's something I would like to discuss in the next video, where we start talking about just very simple systems and see how they behave, and then see if we can extrapolate this behavior to more complex systems. And we'll come to the conclusion that we cannot. And then, of course, the question is, how do we deal with that? Which will be then discussed in the video afterwards. Stay healthy. We'll see each other later.